preceding video, we delved into the question of whether the traveling salesman problem, TSP, is NP complete. Our exploration extended to the traveling salesman decision problem, TSPD, unraveling the concept of NP completeness. In this video, our focus shifts to the Hamiltonian circuit problems, HAM and HAMD. HAMD is an NP complete problem and HAM is an NP hard problem, but the two problems are equivalent in the sense that one can be reduced to the other one in polynomial time. Additionally, we will explore the process of reducing HAMD to TSPD in polynomial time. Before delving into this, let's conduct a concise review of some key terms. 1. A non-deterministic algorithm is one that we can guess a solution to a problem and verifies if the solution is correct. 2. Decision problems are questions that we can answer yes or no. For example, find a cycle in the graph is not a decision problem. Does the graph contain a cycle? Is a decision problem. 3. Class P. P is the class of all decision problems that can be solved by a polynomial time algorithm. For example, does the given list of n integers contain the integer 3? Is a class P problem as we can solve it in linear time by stepping through the list. 4. Class NP. NP here means non-deterministic polynomial time. NP is the class of decision problems that we can guess a solution to the problem and verify if the solution is correct in polynomial time. Note that any decision problem that can be solved in polynomial time is automatically an NP. That is, P is a subset of NP. 5. Class NP complete. A decision problem X is NP complete if it satisfies these two conditions. First, X is in NP. Second, for every problem Y in NP, Y can be reduced to X in polynomial time. This means that if X can be solved in polynomial time, then Y can be solved in polynomial time. Y is reducible to X can be represented by this symbol. Basically, any NP complete problem can be reduced to another NP complete problem. So to prove that a new decision problem is NP complete, we just need to show that a known NP complete problem can be reduced to this new problem. 6. Class NP hard. A problem X is NP hard if there is an NP complete problem Y that can be reduced to it. That is, Y is reducible to X. Note, if Y is reducible to X and X is reducible to Y, then we say that X is equivalent Y. You can see that NP complete is a subclass of NP hard. NP complete class includes only decision problems while NP hard include both decision problems and non-decision problems. It is an open question whether an NP hard problem can be solved in polynomial time or not. If one day someone can prove one of the NP hard problems can be solved in polynomial time, then we can conclude that all NP hard problems are solvable in polynomial time. That is, class P equals class NP, which can be represented by this diagram. Class NP hard is not equal to class P because some of its problems are not decision problems. Conversely, if one could show one of the problems can never be solved in polynomial time, then we can conclude that no NP hard problems can be solved in polynomial time. That is, class NP is not equal to class P. This can be represented by this diagram. 7. The traveling salesman decision problem, TSPD, can be stated in this way. Given a length L, does the graph have a cycle with total length of at most L? For example, in this graph, the length of BE is 3 and the length of BD is infinity. This problem is difficult to solve, but by making an informed guess about a particular path, we can efficiently verify its validity. Therefore, TSPD falls within the NP class of problems. To establish TSPD as an NP complete problem, we'll proceed under the assumption that the Hamiltonian cycle decision problem, HAMD, is NP complete. Now let's delve into the Hamiltonian cycle problem, formulated as follows. Given an undirected graph GV, E, The objective is to identify a path that initiates from a specific node, traverses each node precisely once, and ultimately returns to the starting node. This specific path is commonly known as a Hamiltonian cycle. For example, in this graph, the path 0, 1, 3, 2, 4, 0 is a Hamiltonian cycle. If such a cycle exists, the graph is a Hamiltonian graph. Again, it is hard to find a solution, but if we guess a solution, it is easy to verify whether it is correct. In our discussion, we refer to HAM as the problem of finding a Hamiltonian cycle, and HAMD, the problem of deciding whether or not a graph is Hamiltonian. Note that HAM is not a decision problem while HAMD is a decision problem. We establish the following theorem: HAM is equivalent to HAMD. Let's proceed with the proof. First, we prove that HAMD can be reduced to HAM. This is the algorithm to solve HAMD using HAM. We are given a graph G with a vertex set V and edge set E. The function HAM is given. It returns a graph sigma and knows whether it is a Hamiltonian cycle. If sigma defines a Hamiltonian cycle, HAMD returns true, otherwise it returns false. If HAM, G, finds a solution in polynomial time, obviously, HAMD takes polynomial time to find the solution. Thus HAMD is reduced to HAM. Second, we prove that HAM can be reduced to HAMD. This is the algorithm to solve HAM using HAMD. Once more, let's consider a graph G with a vertex set V and edge set E. The function HAMD is provided, which informs us whether graph G is Hamiltonian. If it isn't, we return no solution, indicating the absence of a Hamiltonian cycle. Conversely, if the graph is Hamiltonian, we ascertain the existence of a solution. Next, we systematically assess each edge. If the removal of an edge still preserves the graph's Hamiltonian nature, we eliminate it permanently. Otherwise, we retain the edge. The resultant sequence of edges, post this iterative process, forms a Hamiltonian cycle for the graph. The time to execute this algorithm is essentially the number of edges times the time to run HAMD. It is polynomial time if HAMD takes polynomial time. Thus HAM can be reduced to HAMD. To illustrate the second algorithm, let's examine a simple example. Consider the given graph, and assume HAMD is provided. The table below delineates the process. Column 1 represents the considered edges. Column 2 verifies graph connectivity post-edge removal. Column 3 indicates whether to remove or retain the specified edge. Column 4 displays some of the current graphs under consideration. For instance, when removing edge AB, HAMD indicates that the resulting graph is not Hamiltonian. Therefore, we retain edge AB. Next we remove AC. HAMD says no, so we keep it. Next we remove BC. HAMD says that the remaining graph is still Hamiltonian, so we remove it and this is the remaining graph. Next we remove BD. HAMD says yes, so we remove it and this is the remaining graph. This process continues iteratively, assessing each edge based on HAMD results. The remaining graph is the Hamiltonian cycle as shown in this figure. So HAM and HAMD are equivalent as they can be reduced to each other. It is widely acknowledged that 3SAT is an NP-complete problem. Furthermore, it can be demonstrated that 3SAT is reducible to HAM. Consequently, HAM is an NP-hard problem, while HAMD stands as an NP-complete problem. Additionally, we can state the following theorem: HAMD is reducible to TSPD. Here's the proof. We begin by assigning a length of 1 to each edge in the given graph G. In cases where there is no edge connecting two vertices, the length between them is designated as infinity. In practical terms, representing infinity can be achieved by employing a sufficiently large numerical value. For example, in this graph, AB equals AC equals BC equals blah 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 equals 1AE equals AF equals BF equals blah 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 equals infinity. Now, consider the traveling salesman problem decision, TSPD, with inputs graph G and length L. If no cycle exists in the graph, TSPD invariably returns false for any finite value of L, as the path going back to the starting point will be infinity. Conversely, for a sufficiently large value of L, example, a value surpassing the number of edges in the graph, TSPD consistently returns true. Here, TSPD is given. The algorithm that utilizes TSPD to solve Hamiltonian cycle decision, HAMD, is as follows. If TSPD returns true, indicating the existence of a cycle, the graph is deemed Hamiltonian. Otherwise, it is not. It is obvious that HAMD is polynomial time if TSPD is polynomial time. Consequently, HAMD can be reduced to TSPD. Recall that we previously established that TSPD is an NP. Therefore, if HAMD is NP complete, it follows that TSPD is also NP complete. This example illustrates how one can leverage a known NP complete problem to establish the NP completeness of another problem. If you find this video helpful, please give it a like. Thank you for watching. Bye.